and attack it head on with whatever questions you guys want me to go ahead and give you guys the basics. Obviously, I'm not going to solve them for you, but we're going to at least kind of give you guys a little bit more of a walkthrough of the tools that otherwise you're going to need to be using, which we've already actually gone through all of them. While we're about to finish up the rest of them today. That's why the assignment is going to be due at the end of the day. But effectively, you know, how we can kind of go about it. So let's have a little bit of fun. So all right. So, you know, the first one you guys have to do is you have to figure out how high the Hulk jumps, which is obviously a guesstimate. And then from there, you have to go ahead and extrapolate effectively. If we know how high somebody jumped, we're going to be able to figure out the acceleration, because acceleration is simply going to be the time from the bottom of their jump to the top of their jump. Now, this is obviously not the exact same thing that you guys did for your class or for your assignment. And this is the not as good Hulk movie if you guys feel like punishing yourself with some older things, but it's going to still give us the same basic components. What we need in the everything that you're going to be trying to solve for is effectively the same. So what we have is the scene is the Hulk literally lands, jumps again immediately, hits the apex of that jump, lands, jumps again immediately, jumps again a little bit, and then so on and so forth. And then, yes, look at that CGI from the early thousands, guys. Now, actually, okay, yeah, it's not going to have, there's a part where he literally jumps up high enough to punch a fighter jet. But, okay, so what we're going to go here is we're going to go to settings, playback speed. We're going to go to quarter time, okay? From there, we're going to go ahead and hit play. So, see the nice little CGI Hulk going and flying through the air. So what we would do is, see how he's just about to touch the ground. We would have a stopwatch, which you can use because there's a stopwatch on your cell phones to figure out the exact time he touches the ground. So that would definitely be the bottom of the jump because he's in the bottom. And he's off the ground again. So that incredibly short period of time, that is going to be where he goes through a velocity of 0 because he's at the bottom where he has no vertical velocity to the second his feet leave the ground where he'll be at that peak velocity, because we're just using the wonderful projectile motion. So that is going to give us the period of time that he's going to accelerate. Now, obviously, he goes all the way up to the apex of the jump, which is probably about there. Now, you don't have anything for scale, like as to how high that was, other than the Hulk's about 8. I think canonically he's like 8 to 10 feet tall, at least in this film. And so you figure he just leaped what has to be, you know, gosh, if you're looking at the size of him, it's got to be well over 100 feet. Now, I don't expect you to have an exact number, but we're just trying to go and figure it out. So then when you're looking at your projectile motion formulas, okay, we don't know what the initial velocity is. So that's question mark, okay? The time would be the time from the takeoff to the time to the point at which he hit the apex of that jump, okay? The displacement, so on the other side, that's going to be equivalent to, we'll say about 40 meters. You guys can go more than that. This is just a real quick and dirty ballpark, but that's what I want to expect you guys to do, which is work your way through it and think it through. So then effectively in this example, you'd have 40 meters equals a V sub O, which we don't know, the amount of time it took him to fly up to that apex of his jump, which looks like it took a little bit over about 2 seconds from the timestamp because he took off from the ground at about 3. Okay, so times 2. Then it's gonna be minus 1/2, and this happens in the Marvel universe, it's Earth, so it's 9.81 meters per second squared gravity multiplied by 2 squared. And from there, you're going to be able to figure out what would have been that initial velocity to get him to be that high. In fact, if we really want to do it perfectly, all we'd have to do is keep press and play and let this run until he hits the ground, because then we're going to be solving through 0. And that actually is going to give you your exact, then you're going to be able to figure out the mid-flight time, so it's even better. So then you figure, and he lands just shy of, gosh, leaping through the air for almost 6 full seconds. Geez, that's a lot of time in the air. So that's how you solve that one. Now, well, that's what the initial velocity is it's going to be what he's taking off with. And so if he starts at the bottom of the jump, guys, you all have a vertical velocity of 0. You're just stopping holding a position. Now it's as you jump off the ground, that's where you now have a positive velocity. And so you subtract it by. I've said a lot of things, so I'm not exactly sure what you're referring to. 3 horses. 4 parsecs. Oh, it's the formula that we've been using all semester long, guys, with our projectile motion. So just it's literally this formula we've been using the entire time. So then the other scene where we're talking about the Mr. Incredible, then you have to try to get an idea for how fast he would have been going. So now we're looking at velocity, power, we've got our mass component, or for work, sorry, we've got our force component, mass times acceleration. We're just assuming it's Earth gravity. Obviously, it's a cartoon universe. It could be more, it could be less, but we'll just figure it's going to be that. There is a way that you could figure it out mathematically if you really wanted to, but that's going to be a real pain in the butt. You have to figure out how fast the characters fall and then extrapolate that based upon known distances and then plug that through the same type of displacement formula. This is not meant to be easy, guys. This is meant for you guys to really sit down, think through logically as to what's going on and what you're effectively going to be seeing. So for the other, when we're looking at, so then you just Google like how much does a train car weigh? Then you figure out how many train cars he was pulling. So now you've got the mass of all that. Your acceleration is going to be effectively is overcoming the acceleration of gravity and whatever the coefficient of friction is, which is something that we're going to wrap up by the time we get done today. So you've got the basics of how we work with friction, along with you're going to be obviously figuring out simple things like kinetic energy. Pressure is already out there because if you know the mass of a train car and then the surface area of the hand lifting it, you're going to be able to extrapolate what that's going to be placed across. Feel free to work on this also in groups, guys. It's meant to be difficult. So, all right. Now we're getting into what's known as energy. So effectively, the first one we have is going to be what's known as kinetic energy. So this is the energy that something has while it's moving, and this is going to be in the units of joules. Okay, so these are Newton meters. So once again, we're talking about a form of work. Okay, so when an object is in motion, it has what's known as kinetic energy. Okay, kinetic energy is going to equal half of the mass of the object multiplied by the velocity it's traveling squared. okay? We then have what's known as potential energy. And this is going to be the energy that something has that can be released when it's dropped from a height. So if I have a book sitting at the top of a shelf, it has potential energy. If the book falls to the ground, as it's falling, it's losing potential energy because it's not as high off the ground. However, it's gaining kinetic energy because obviously it is going faster and faster as it accelerates in the floor. And then whenever it hits the floor with 100% of that energy being converted to kinetic energy. And, you know, if that happens to be your big toe underneath it, it's probably going to be pretty uncomfortable. Now, this is an easy way that we can extrapolate how high somebody jumped, because if we know the mass of the object, the gravity it's undergoing, and the height it managed to jump to, that is always going to be equal to the kinetic energy it had whenever it was jumping off the ground. So if you guys are going, you dip and you jump as high as you can off the ground, right when you're leaving the ground, you've got that peak kinetic energy. Now that kinetic energy is converting the potential energy until you get to the top of that jump, and then it's converting back completely into the same kinetic energy you left the ground on, as long as you're obviously taking off and landing the same height off of the ground. So why we care about this? Because just like momentum, it is another form of energy that is going to effectively be distributed between two objects. Now, momentum is going to be effectively the energy something has while it's going, obviously, in direction. But kinetic energy is going to be effectively a more accurate idea of the amount of work you need to produce in order to get it to that speed. And higher speeds require a lot more velocity, and velocity is the more powerful contributing factor of the overall speed or the kinetic energy that something is going to be having to produce. Now, strain energy is another type of potential energy, and this is effectively coming from kind of an elastic rebound effect. So think of like tennis rackets, think of bow and arrows. And so what's going to happen is our strain energy is going to be equal to half the volume, so effectively the surface area otherwise that is being distributed over, multiplied by the stress and multiplied by the strain. Now, there's also another version where you can go half the volume by Young's modulus, which is going to be a set number, and then the strain upon the object. So if you think about a bow string, when you pull it back just a little bit, it doesn't really have a lot of energy to fire that arrow with a lot of speed, but you keep pulling back further and further. Now we're going to go ahead and increase that strain energy that's being distributed through the bow. And obviously compound bows use leverage to make things a little bit differently on flywheels. But if you're thinking about it typically like a recurve wooden bow or like a slingshot, so the further you pull it back, the more power or more energy you're going to be storing in there that will then be released and then boom, converted over into kinetic energy. Hence the speed of the missile one will launch from them. So what can you guys think of would be examples, and I know you can kind of see it if I move that up, where you're going to have kinetic energy, potential energy, and strain energy, all in the same movement or performance. What can you guys think of? Anybody? Yes, great job, Kristen. Trampolining, awesome. So you're converting back and forth between two. Now, raising a hammer is going to be more potential energy and kinetic energy. Strain energy, if you're hitting it hard enough that you're actually putting a bend in the actual object, in the hammer shaft itself, that's intense. Hitting a baseball bat or hitting a baseball with a bat, potentially. The bat and the ball will have a little bit of strain energy upon contact, where there'll be kind of, there's a little bit of deformation. Now with pole vaulting, absolutely. And yeah, with bouncing basketball. Great job, guys. Awesome. I was afraid that my connection was bad because I didn't see anything and I was feeling kind of lonely. So another one is diving off of diving boards. And then I'm glad you brought up the bouncing of a basketball, Marlana, because that brings us to the wonders of rebound. Okay. Now, every object, whenever you try to bounce it off the ground, has a differing amount of rebound. So if one of my cats was to come over here and I was trying to bounce her off the ground, because it's probably going to be Tinks, and no one's female. Now, first and foremost, we're not going to do that because that's a horrendous thing to do to an animal. But it turns out cats, like humans, we don't really bounce that much whenever we hit the ground. Whereas obviously things like a basketball, like those rubber balls that you guys would use in your younger lacrosse balls, those have a pretty high coefficient of restitution. Now, this is an important component to keep in mind because it lets you know how much of the energy effectively is getting essentially transferred back into from strain energy into kinetic energy to get the object off of the ground. So if any of you guys have ever seen clay getting thrown at the ground or otherwise, silly putty, Play-Doh, it just hits and distributes. It doesn't really bounce. And then obviously the opposite can be true. Now, when we're looking obviously at different types of sports, that hence the hitting a baseball with a bat, you're going to see that strain energy because we're going to be deforming the object. And in turn, it is going to then essentially expand again and fire off in the direction you swung and hit it through. Now, obviously, there is a true exchange of momentum between the club head and the ball itself. Now, what's going to happen is, specifically when we're talking about something like a golf ball, this transfer of energy is also going to be released as heat. It's another form of power. And this is now we're talking about, once again, kilojoules of energy. And in turn, what we find is when things heat up, they tend to improve their ability to have rebound. So that's why in the sport of squash, they literally pass the ball back and forth for a while before they play the game. So that way the ball is going to play more uniformly and play better off of the wall. Now, there's a number of other components that are going to affect rebound, not just the temperature, but obviously the elasticity of whatever you're playing with, the angle and the velocity that object is going to go ahead and hit with. I'm sure all of you guys have seen somebody bounce off something because they got essentially pushed into an object at a very high speed. And then the amount of spin along with friction between the surfaces. So, for example, if you're going to go and try to slide in sand, you tend to slide and not really bounce. But if you're trying to, well, hopefully you never try to slide across concrete or asphalt, but if you've been there, you realize you actually kind of bounce a little bit when you hit. And that's simply because it turns out that friction between you and the surface, along with obviously the type of rebound you're getting between those two objects touching one another. Now, another component to keep in mind when we're looking at projectiles is to understand what's going on with spin. So effectively, the way that a ball is spinning, or an object is spinning when it hits a solid surface, it is going to cause it to then kind of careen off in whatever direction it's going. So hence, top spin, when you're talking about tennis, the ball will hit and then jump forward. But side spin will hit and then take a curve, whatever direction it's spinning. And then finally, whenever you're going to backspin, it'll hit and then potentially come backwards, or at least lose pretty much all of its linear velocity that it was currently traveling on. Now, finally, we get ourselves to friction. Now, friction is going to simply be the total frictional force is going to be equal to the coefficient of friction. So that essentially is how strong is the friction between two surfaces, and what is known as the normal perpendicular force. And that is the force directly pulling the object straight down. So the only thing we need to know is effectively what's the amount of force that's pulling directly down into the surface, and effectively what's the coefficient between the two. Now, this is something that can be a little bit more difficult for some folks to grasp, and that's okay, That's why we're going to take our time, go through it. You guys have to ask questions, okay? So the greater force we have pushing down, so that's that normal perpendicular force, perpendicular to the surface. So if we're on an angle, it's going to be the force going into that plane. If we're flat, obviously it's the force going straight down. That's what it means by the perpendicular force to the surface. Now, when we're looking at this example where it's just a sled sitting on top of, I'm guessing, what would hopefully be some ice or snow, it doesn't have a huge amount of normal perpendicular force. But if we add a kid to it, now we've increased it. If we add a dog on top of it, now we've increased it even more so. So effectively, the amount of force we'd have to push on the object to overcome the total friction, even though the coefficient of friction doesn't change at all, it's just the normal perpendicular force that's changing, is going to increase, okay? That's why it's easy to slide in or to move like an empty cart that's on wheels, because we have rolling friction, which we'll get into at the very end here. But as we go and try to push something faster and faster, or push something that's heavier inside of that cart, we now have a greater normal perpendicular force, and now it's harder to move. Now, another component to keep in mind is going to be the effects that we have of pushing an object. So like right now, my computer is sitting on a table. If I was to think about pushing down and towards the table, I'm thinking about force vectors, guys. I'm going to be pushing horizontally, but I'm also pushing vertically downward. And because of this, I'm actually increasing that perpendicular force. So I'm actually making it harder to move the table. In fact, you guys can try that at home right now. If you've got a table, you're near a desk or otherwise, try pushing downwards and away from you and feel about how much force you have to push with to move the table. And then do the opposite. Grab the table and pull it towards yourself. So I'm lifting the table upwards. So I've got a vertical vector and I now have a horizontal pulling it towards me. And since I'm pulling in that angle, it's actively decreasing the total frictional force I have to overcome. That's why it's easier to drag a sled towards you or pull the sled towards you than it is to try to push it on those low handles, because we're actually actively making the sled a little bit heavier by doing so. Physics is a harsh mistress sometimes. Now, we have effectively 3 different types of friction. We have sliding friction, okay? That is going to be when an object is actually in motion, okay? This is going to be the lowest friction we encounter. We have static friction. This is going to be the amount of force you have to overcome to get the object to move in the first place. And this is why if you've ever tried to move a really heavy object and just try to slide it a couple inches, it's a real pain, because the second you get it moving, it then is a lot easier to keep moving. So because of that, it's really easy to overshoot what was your intention of where you wanted it to be. And then finally, we have rolling friction. And that is going to be the resistance to a central movement, an object, for having it roll over a surface. So some examples. If we have a box sitting on a surface and we want that box to move, when we try to push that box initially, because it has its perpendicular force and has its coefficient of friction, we have to overcome that initial force in order to move it. So we can push it and it won't even move at all. But if we push a little bit harder, eventually we're going to overcome that static friction, and now we have it moving. And then it immediately, as soon as it's moving, converts into sliding friction, aka kinetic friction, and it's going to be a lot easier for it to stay in motion. So if we're thinking about looking at just the sheer force that's going to be applied over time, we're going to see that force increasing until we hit that, notice that point where we overcome static friction. And then boom, dynamic friction is markedly lower, usually a 1/10 of a point. Friction is usually between a 0 and 1 value. So whenever we're trying to move, keep in mind, you have to be able to produce effectively, you have to have better friction between what you are pushing off of than the object that you are trying to move. So effectively, if you are not able to get traction compared to the surface that you're pushing along or trying to drag behind you, you're going to be essentially pushing with no effect. And since we're currently in the wonders of winter, and there's obviously always the chance for more snow, what you're going to find is obviously there's situations where you might try to have to push out a car otherwise. And if you can't get traction, aka you're not able to get enough friction between you and the ground, whatever object you're trying to move is not going to happen. And this is something that definitely happens whenever you're trying to push somebody out of bad conditions. Now, rolling friction is going to effectively be the coefficient of friction we're having between the actual object that we're rolling along. So this is not just related to the coefficient of friction and the normal perpendicular force, but also literally the diameter of the round object that's trying to obviously roll along it. And so what we're going to find for improving our rolling friction, so the better job we do of actually gripping the object, which causes more resistance to movement, but also increases our traction, so it decreases our chance of sliding, is having not just better tread, but actually lower tire pressure, so more of the tire touches the ground. And then you can obviously add chains, add gravel or something else in order to help improve it. Now, we can also just increase the weight of the object, so we increase that normal perpendicular force. That's why people put sandbags in the back of trucks whenever it happens to be getting more winter, to make them drive a little bit safer. And actually, of all things, but using a smaller diameter tire actually does help with increasing our rolling friction. Now, if you want to decrease it, which is going to effectively make your car arguably a little bit more efficient, you want to go ahead and effectively use tires that have a lower amount of tread, a smoother road we're going across, and higher tire pressure. And that's a way to do the basics of what's referred to as hypermiling. So we're effectively trying to get more miles per gallon out of our vehicle. And we can also do this by trying to make the vehicle lighter, carrying less weight, and using larger diameter wheels is actually going to go ahead and help enhance this. So those give you all of the tools that you're going to need in order to effectively figure out what is going on with our wonderful math problems that we've given you guys for the superhero homework. Now, what questions do you guys have for me before we're going to give you guys a couple little group things to do? And then we're going to be reviewing hard for our upcoming class. Now, what's cool, if you're talking about coefficient of friction and changing normal force, give me 1 second. So my wife and I enjoy board games. So here's one you can play when you can actually be around other people. It allows you to really distrust people. This is just a piece of foam, okay? So right now, this foam is in touch with this surface, so they've got the coefficient of friction. So it doesn't require a lot of force, and I can move it across. But notice the two are adhering. Now notice I'm tilting it. So whenever I tilt this, the normal force is what's going straight into the box, but notice gravity's pulling this straight down. So we've got a force vector, one that's going perpendicular, one that's dragging it down. So as I tilt it more and more, eventually notice it slides. And that's because the force vector going down is greater than the force vector keeping the two in contact. So if I do the same thing with a rubber band, okay, coefficient of friction here is going to be different. Notice I've got to go a little bit further before it's going to go ahead and slide off. And then I feel like it'd be kind of entertaining if I could get the cat to stand on it and see how that goes. No, I'm kidding. But that's what we're looking at when we're seeing that coefficient of friction, the normal force, and how it changes with angles. But okay, you guys are pretty quiet.
Right. For the Hulk question, do I need to Google how much the Hulk weighs and how tall he is to help figure out the question?
Absolutely. That is definitely options you can do. You definitely want to figure out, the weight of the Hulk. And that's one Google search away. Usually it puts them at like 400 to 500 kilograms.
It was like 1,400. And then, yeah.
Yeah, just make sure you're doing that in the metric units. Mm-hmm.
Okay.
Good, Colton. What would be, what's a good option that's not too dark for you guys? Mhm. Okay, so when we figure out the force for the Hulk problem, you got to keep in mind force equals mass times acceleration. He's not just overcoming the mass or the acceleration of gravity, but he's also got the acceleration of his body moving to get up to that velocity. Okay. Please put your questions the into the general chat, because I've got one student who's asking me questions, but no one else can see it. Now, you do not multiply the acceleration due to gravity and the acceleration of the jump together. No, 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 that is Fruit Loops. Instead, you've got the acceleration of gravity, which is pulling us down, and the acceleration going up. So the key is we had to overcome that negative 9.8. So we add the two together and then multiply that by the mass of the Hulk. So let's say you've got effectively, you've got the acceleration of gravity at 9.81, and let's say you come up with he had to accelerate himself at 41 meters per second. So the actual acceleration you guys would use would be that 50.81. Then take that 50.81 and multiply that by the body mass, and that's going to give you the force that actually was produced. All right, so I'm going to have you guys, I'm going to put you guys into groups, and we're going to do a potential energy and a kinetic energy formula, because both are going to be used here. And if you really, and actually we're going to go ahead and figure out the force applied. So what you guys are going to do is so at 22:28, yeets himself out of the window, falls what looks like a considerable distance, hits one object, and then bam, hits the ground. And is somehow fine. So that's cool. So now you have to figure out, okay, how fast would he have had to be going? And you can go and how much force you would hit the first object with. Okay. And then again, what speed he would have gotten up to when he hit the second object. Now, obviously he careens through it. The math is going to get muddy. You just do your best to kind of guesstimate what you think that would be. But that gives you something to go ahead and take a look at. Questions, comments, concerns? Okay, so it is 10:06 now. I'm going to give you guys some quality time. So we figure this is Earth gravity, so gravity's going to be 9.81 meters per second squared. But trying to figure out the height of the building, the weight of Captain America, and all of the in between, that is going to obviously be a challenging component. But do your best. If you want to, you can time how long it took from jumping out of the window to hitting the first object, and then take the time again from hitting that object to hitting the ground. And that's going to give you some ideas of the acceleration you would have had, and even the force we could extrapolate because of the differential of the extra falling time with effectively how much energy it would have taken to break that window above. Talk with each other, guys. Work through your math and try to have some fun. Okay? Get after it, and I'll see you guys in a few. So, yeah. Potential energy converts to kinetic energy, figure out the time span for each of those, figure out the impact period of time, and you're going to be able to figure out all these. I realized I wasn't recording any of that review, so whoever's watching this later and trying to do it is going to be mightily confused, but they'll figure it out. But otherwise, yeah, the kinetic energy stuff you guys did, that looks great. It's the force on impact still looks a little low, and that's okay. You guys are learning. So remember, one more time, we go from yeeting ourselves out the window. So start, then we have the first time period of stop, start, and then stop, start, start of literally that first touch and the bounce, and that's going to be literally all the absorb. Yes. So it's definitely that 50.8. Absolutely, Kristen, where you have to overcome it. Okay. So think of it this way. Okay. In order to hold this glass of water up, okay, I have to overcome the acceleration of gravity. So if I want to lift it higher, I have to produce more force than just what gravity is pulling upon it and create my own acceleration to move it upwards. Okay. The second I hold it and I produce less force than what gravity is pulling down on it, obviously it's going to go downwards. And I could spike it and pull it even faster and slam it into the ground. And if I did that, then I got my negative acceleration on top of the negative acceleration of gravity pulling it into the ground. All right. So in theory, but seeing as how there doesn't seem to be like a giant like crush on the sidewalk there from the amount of force you would have put into the ground, especially from having a vibranium shield, or maybe it's adamantium. I don't remember anymore from what it is canonically. I think it might be vibranium. That, yeah, that would jack some stuff up. So last thing we're going to go ahead and have you guys do, and this should hopefully be a bit easier, is figure out what would be the actual force you need to move a 200 kilogram block of made of iron, okay, across a wood floor, a concrete floor, a carpeted floor, or, oh, sorry, group floor. Congratulations. You guys are going to go ahead and have, we'll give you guys ice. How much force do you actually need to produce on just a pure horizontal vector to overcome the frictional force both static and then dynamically. So you're gonna have to Google what is the frictional, what's the coefficient of friction between this and this, static and dynamic. Or they could say static and kinetic. So just keep that in mind. Okay, so this should hopefully be a bit easier. It's 10:35. We'll plan on coming back at about 41 or 42. What do you guys come up with? Yeah, Anna, which you guys use ice. So remember, you're going to take 200 kilograms. You're going to multiply that by 9.81. So that's going to give you the normal force. And then you're going to multiply that by the coefficient of friction you chose. So if you see here, you know, steel and ice is super low. So you'd actually, in this example, you'd move it, multiply by 0.03, but you'll find other examples of this type of friction in other spots. So then we go on up. Colton, that is possible. So notice, guys, we got cast iron here. We've got oak, which obviously is wood. So we're going to say clean and dry. So you multiply that by 0.49, and that's the dynamic friction, not the static friction. So that is one of the limiting factors, is it can be kind of hard to find exactly the example that we're looking for. So, but that's the basic idea, is you look through and try to figure out what would actually be the coefficient of frictions between the surfaces. Yeah, so for the static and then the dynamic. Good. So notice, guys, the static is going to be higher. Effectively, you need to find the dynamic factor 1. So for example, once again, for you guys, we could use this right here. If I come over to the top, notice, guys, that's the kinetic, the sliding friction, and then the static friction. So hence, if we were to say it was brass and steel, notice, guys, we'd have 0.51 for the static. So we'd multiply the normal force by that. But then when we're going to go with the dynamic, now we're going to go ahead and multiply that by the 0.44. So don't freak out, guys. Keep going through it. Work on those. Work on your homework. Think it through. You can figure out everything you need through just Google searches away and then timing it yourself and using other known objects. Like when he's pulling the train ties are actually set at a uniform distance from one another. So if you know how far a single train tie is from another one, for how many train ties he follows, recovers in a second, you can figure out the distance between two. You now have velocity. Congratulations. You can figure out power. But you have to think critically about it and ask myself, what do I know? What do I need to figure out? All the answers are there. You have all the tools you need. The problem is you have to figure out, okay, what tools do I use? So stay safe out there, guys. Keep working hard, and I will see you guys back on Tuesday. And next week is all review for your exam, which is the following week. So have a great day, guys. We've gone over. Sorry about that. Bye-bye.